Okay. All right, so let's get started. And this first part of the class is kind of extraneous, which is why I'm just going to start earlier, and people can run in or watch the video. So we're on diffie-q's now, and I'll get to them, but we're going to talk about first the matrix exponential, which is an application, technically an application of diagonalization. We'll see this later on I guess, maybe in chapter 9, but the reason why I'm bringing it up now is because if Davi just introduces this out of the blue, like a week before the midterm, it'll likely be on the midterm. So we're gonna talk about it now rather than later. So, right, in general, A can be written as SDS inverse if A is diagonalizable, and that really shouldn't be like a contentious claim at this point, right? So we know that, okay, A, you can write it as this basis of eigenvectors, a diagonal matrix, and then the inverse. And, okay, so the matrix exponential is this thingy, e to the at. All right, and what is e to the at? Well, you have e, right, and you're raising it to a power, but it's a matrix in the power, right? It's not just some constant in the power. So it's not entirely clear then what you're supposed to do. One way we can solve it is if you remember your Math 104 or your Calc BC days, where you had e to the t, and we could Taylor expand e to the t, which was 1 plus t squared over 2 factorial plus t cubed over 3 factorial, et cetera, right? So that should be kind of familiar. So we can do the same thing with e to the at. We can Taylor expand it about at, and what do we get? Well, okay, instead of getting 1, we would get the identity matrix, because you don't have a 1 in matrix form, right? So you got the identity matrix. You'll add at, and then everywhere you see an at, it becomes like at squared over 2 factorial, at cubed over 3 factorial, et cetera, right? So that's one way we could calculate the matrix exponential, e to the at. And if any of you guys are like me, you haven't done a Taylor expansion in like years or don't remember how to do one. So we usually don't deal with this Taylor expansion, e to the at. So what we do instead is we use the fact that A is diagonalizable, and we can write then e to the at is equal to s times e to the dt s inverse. Okay? And the reason why we can do this is kind of like the same reason why, like, remember when we have like a to the power, so like a to the k is equal to s d to the k s inverse. We like kind of exploit the same property there. Okay? So, all right, so we have e to t is equal to e to at is equal to s e to dt s inverse. So let's take a look at an example then of what this actually is. So let's determine e to the at if A is equal to 3, 3, 5, 1. Okay, so what do we want to do? Well, it looks like we want to diagonalize this matrix first. So characteristic polynomial, determinant of A minus lambda I, is equal to the determinant of 3 minus lambda, 3, 5, 1 minus lambda, which is then 3 minus lambda, 1 minus lambda, minus 15. And that should be lambda squared minus 4 lambda minus 12, set it equal to 0. And then you get lambda minus 6, lambda plus 2. And so our roots then will be 6 and negative 2. Okay. Now we need to find eigenvalues and eigenvectors. So let's let lambda equal to 6. We take a look at the matrix. You get -3, 3, 5, -5. And so what is an eigenvector associated with this matrix? Yeah.
1, -1.
Not -1.
1,
1, 1. Right. Same sign.
Oh, yeah.
So 1, 1. So that's going to be an eigenvector. And then we can take a look at lambda is equal to -2. You'll get 5, 3, 5, 3. All right. And then the second eigenvector, well, they're the same row. So we'll just do -3, 5. Okay. So now what? So now we have SDS inverse, right? Which is 1, 1, -3, 5. D is 6 and -2, right? Because the first column responded to lambda equals 6. And then S inverse, I'm going to use the determinant 2 by 2 trick. So this is going to be 1/8, because so 8 is the determinant of this guy. And then you flip the diagonal, and then you take the negative on the off diagonal. So that's S inverse. Okay? And now e to the AT is equal to S e to the dt S inverse. I know what I forgot to say. I forgot to mention what dt is. That's fine. So what is okay, so S remains the same. What is e to the dt? If anyone had to go out on a limb and guess what e to the dt is, what would it be? Any guess? Yeah. So almost, right? But we have this e to the power thing. Yeah, raise the diagonal to the whatever times t, right? So this is e to the 6t and e to the -2t.
Why is that? Just saying it's.
Yeah, I'm just showing you that you're taking the negative of the off the diagonal. Yeah, so that's why. Okay, and then you have your inverse matrix 5, -1, 3, 1. Okay, so again, e to the dt, not hard to find, which is why we do this. Especially like once you have the diagonal matrix, you have e to the dt, right? It's one step away. So okay, so now for 2 by 2, you're going to be asked to like multiply this out, but I'll just trust that most of you guys can do matrix multiplication at this point. So 5e to the 6t plus 3e to the -2t, 3e to the 6t minus 3e to the -2t. Oh yeah, there's a 1/8 out in front. 5e to the 6t minus 5e to the -2t. 3e to the 6t minus 5e to the -2t. Any questions? Besides, what the hell are we using this for? All right, so let me answer my own question then. Why are we even doing this? If you look at your differential equations notes from the past 2 lectures, right, what have the solutions to your diffie-q's all look like? Exponentials, right? You have like some constant times e to like something, some power with like t's in it, right? Okay. So we have a bunch of them here and we have them in matrix form. So this matrix exponential, it's used to solve a system of differential equations, all right? So what we're doing right now is that we're going through one at a time when we're solving one differential equation at a time. Once we get to a system of differential equations, which is the next chapter after this one, this is the way to solve those systems. And so I think Davi was planning to introduce it there, but like it's good to see it here first. Okay. Do we want to go through another example or no? Not really? Okay. So let's then jump. So in the previous recitations, we went through a 3x3, but it's the same case, right? You diagonalize it, you raise it to the whatever power, and then you just multiply them together. So now let's just jump into diffeqs. Or really ODEs, which stand for ordinary differential equation. Okay, so what? So here's the toolbox, which is really all the vocabulary I'm going to be using for this section. Okay, so you have an ODE. So I'm going to write a general one. AY double prime plus BY prime plus CY is equal to f of x. Okay, so what is this? This is a second order differential equation. All right, and the reason why it's a second order differential equation is because I have a y double prime. All right, so the highest power derivative tells me what order my differential equation is. Okay. We can write this analogously as AD squared plus BD, that looks like a 6, but it's a B, plus C applied to y is equal to f of x. So what is D? D is the derivative operator or the derivative map. All right, so D is a linear transformation that takes some continuously differentiable function on an interval and it makes it one time less differentiable, all right, by taking the derivative. So that's what D is. All right, your book will refer to P of D. This is the polynomial in D. So the polynomial in D is going to be this guy in the parentheses. That's P of D. Okay. What else? So in this polynomial, right, you have A, B, C. These are coefficients. And the kicker is that they're not necessarily constant. I don't know how to spell. Is there two S's? Okay, so ABC, for the purposes of this homework and for the purposes of introducing diffeqs, they're going to be constants. But every diffeq you'll see on your exam, well, not every, I'd say like 90% of the diffeqs you see on your exam, actually that's not true either, but a good majority of the diffeqs you see on your exam will not have constant coefficient constant coefficients. That's what I'm trying to say. So keep that in mind. Okay, what else? F of x. F of x is the right-hand side equation, or right-hand side function. So I'll almost exclusively refer to f of x as just the right-hand side. I'll just say it's the right-hand side. But I'm really talking about the f of x here. And if f of x is equal to 0, we have a homogeneous diffeq. And if it's not equal to 0, we have a non-homogeneous diff-EQ. So that should be familiar, right? Because when we're talking about systems of equations, we had homogeneous systems of equations and non-homogeneous systems of equations, which were the exact same thing. Like you had the right-hand side either be 0 or not 0. Okay, so that's the f. That's f of x. What else? You have y. Okay, so y or y of x or y of t. So one thing I didn't mention is that this x, it could be t. It really doesn't matter. It's just some function of some variable. It could be f of quotation marks, and then you can just call your quotation marks as your variable. It doesn't matter. So whatever you choose for f, whatever variable that is, you got to choose it down here. So this is your general solution. Okay. But y of x or y can be written as yh plus yp, where you have yh is your homogeneous solution. All right, so yh is the solution to the homogeneous equation, and there's always going to be the number of, actually, how should I write this? So yh is equal to y1 plus y2 plus whatever, yj, and this j is just the order of your differential equation. Okay, so if you have a second order differential equation, you're going to have two separate solutions for the homogeneous. Okay, so this is just the order of the diff-EQ. And then all of these are linearly independent. Yeah.
Wait, sorry, so what is one element in y? What's y?
If your solution was c1 e to the x plus c2 e to the negative x, then c1 e to the x is y1, and c2 e to the negative x is y2. Okay. Yeah. And when we go through examples, I'll point that out the first time. So right here, this is all done in abstract. Okay. Yp is the particular solution So what does that really mean? It means that if you plug it in, into the diff-EQ, you'll get f of x. All right, and the particular solution, it's kind of difficult. It's difficult to deal with. So in this recitation, we're not talking about it. The rest of this course is how do we deal with this particular solution. So for now, I think for this homework as well, I think it's only on sections 8.1 and 8.2. Right? I don't know if people have taken a look, but 8.1 and 8.2, we're not dealing with particular solutions for now. So. Okay. And so why the particular solution? It could be a linear combination of a bunch of terms. It could be just one term. It really doesn't matter. It really depends on what your right-hand side is. Okay? But homogeneous will always have the same number of linearly independent solutions as the order. So that's more important to know. Okay, did I get through everything? Yes. Any questions?
You said there were multiple homogeneous solutions? Or do you mean the same one solution with multiple terms?
Yeah, it's a linear combination. Well, actually, so each one of those y1s and y2s, they're going to be a solution.
Oh, okay.
they are a solution to the homogeneous, but the homogeneous solution then is the linear combination of all of them. Any other questions? Okay, let's jump into examples. All right, y1. So they're going to be determine the general solution to the differential equations. So number 1, we're going to do y double prime minus y prime minus 2y is equal to 0. And for the purposes of today, it's always going to be 0 on the right-hand side. Okay, so what do we do? So we break this down first into that polynomial in D. So what did I do? I just took the coefficients right in front of y double prime, y prime, and 2y, and then I just chucked them in as a polynomial. And again, you see that, okay, y double prime corresponds to d squared, right? Because d squared acting on y means take 2 derivatives of y. And so that'll get you that guy up there. So now what? That's equal to 0. But do we really care if y is 0? Not really, right? That's like the trivial solution, right? It was like the same thing with like null spaces. We didn't really care if x was like the 0 vector. Okay? So again, we don't really care if y is 0 here. So now what we do care about then is if d squared minus d minus 2 is 0. Okay, and here I'm just going to sidestep a little bit. You don't have to write this down, but I'm just going to point out, and it's recorded, that the book is going to transform this into r squared minus r minus 2 is equal to 0, and they're going to call this a polynomial in R. There's really no need to do this, right? It's like, okay, it's like not proper to have like d, which is a map, like get factored and have roots, right? Because what's the root of a map, right? Doesn't make sense. So then they just like call that R, and then you get like roots in R. But like we really know like what's really going on, and we really only care about what the value of the roots are. So you can just factor that d polynomial, like it's fine. So don't do what the book does and like writes this in R. So we're just gonna factor this d minus 2 d plus 1. And then my roots are going to be -1 and 2. All right, and then so what's my solution? So this is a homogeneous equation. So yx is just going to be equal to yh, which is going to be c1 e to the negative x plus c2 e to the 2x. Okay, and you see that this root ends up here, and the second root ends up in the other exponent. Okay, and so this is what your homogeneous solutions will almost always look like for constant coefficients. And the reason is because, right, if you take the derivative of e to the x, you're going to get e to the x back, and so we kind of just exploit that whole derivative. Okay, and then just to be consistent, just to point it out once, this will be y1 and this will be y2. And since the right-hand side is 0, yp here is technically 0, but like we don't include it, right? Okay, let's look at another one. It's going to be the same thing. So y double prime plus 5y prime plus 6y is equal to 0. So now we get d squared plus 5d plus 6 applied to y is equal to 0. If you factor the d polynomial, you get d plus 2 plus and then d plus 3. And then so d is equal to -2 and -3. And your solution then is y, and because I can, I'm going to say y of t, just to show you guys that whatever you call that variable, it doesn't actually matter. c1 e to the -2t plus c2 e to the -3t. Any questions? Okay, number 3. Got y double prime plus 10y prime plus 25y is equal to 0. Okay, so now d squared plus 10d plus 25 applied to y is equal to 0. And I've just given us the same problem over and over again. D plus 5 squared applied to y is equal to 0. I guess you can drop the y. D is equal to -5 with multiplicity 2. Okay, what's my solution? Yeah. So,
Oh, are you talking about this?
yeah, like what's the general solution? Does anyone have any idea?
cy e to the -x
Yep.
plus c2x e to the -x.
Wait, x, where did that x come from?
That's multiplicity of 2.
Okay, so
So
yeah, that's good. That's a good enough explanation. Yeah. So this is the correct solution, right? Where it's c1 e to the -5x plus c2, and then you have this weird factor of x here, times e to the -5x. And the reason why we need that x is because our homogeneous solutions, right, need to be linearly independent from each other. Okay. So if we didn't have this x, don't do that on your paper, but just hypothetically, if we didn't have that x there, those two are the same thing, right? Like they're just a constant multiple from each other. Like I could write c1 plus c2 e to the -5x, and then I would just rename this to be c3 e to the -5x, and then we're left with one solution for a second order diffie-q, right? And we can't do that. So to remedy this situation, we add in the x to make it linearly independent. Yeah.
So if the multiplicity was 3, would we add like an x?
Yeah, we would add an x
Just
to
keep
it.
going.
So I was going to get to that, but we're going to take a little bit of detour. All right. And so just in general, determining the linear independence of solutions or functions. So I ignore this in chapter 4 or 5 because I knew it was going to come back now. So if we just had like c1 e to the -5x and c2 e to the -5x, that's like pretty obvious that they're linearly dependent on each other. But like in general, like if something was not as obvious, like how would we be able to find out? And so that's where we introduce then this thing called the Wronskian. Right? It's like a top 5 like best math word you'll learn, the Wronskian. All right, so what is the Wronskian? Okay, so it's like really y of y1 and y2. So again, think of each one of these with the constants as y1 and y2. And that's equal to then straight line brackets because we have the determinant of y1, y1 prime, y2, y2 prime. Okay, so so let's just do this example that we have right here. So y1, just drop the constant. So we have e to the negative 5x, and then you have negative 5 e to the negative 5x, and then y2 is x e to the negative 5x. And then down here, there's some nasty product rule BS that you have to deal with, but you end up with 1 minus 5x e to the negative 5x. Okay, so now we take this determinant and we get so the first diagonal, it becomes 1 minus 5x times e to the negative 10x. All right, because when you multiply e to the whatevers, you add the exponents together. And then you subtract negative 5x e to the negative 10x. So that's the diagonal going the other way. And we'll notice then that's just really, it's really like e to the negative 10x minus 5x e to the negative 10x plus 5x e to the negative 10x, which is e to the negative 10x. Okay, and the important thing is that can e to the negative 10x ever be 0? Right? Because if you look at it, remember the exponential graph, right? It asymptotes towards 0, but it's never actually 0. So this thing's never 0. So this thing is linearly independent. All right? So you know that y1 and y2 are linearly independent because that your resulting determinant can never be 0. Okay, if it is 0, so use a different color here. If this were 0, then it would be dependent. Okay, and I think it has to be 0 everywhere. So like literally that determinant would have to be 0. So it's not like you can choose a point to get 0, right? Because your determinant's a function of x, right? Like if you could choose a point x that made that 0, whatever, but if it's everywhere 0, then it's not good. Okay, so the next thing, a logistical thing to ask is, okay, what if you have more y's, right? What if we had like a third order diffq and we want to see if they're linearly independent? Then you would just do like y1, y2, y3, and then you would just have to take derivatives up to the double prime. So then you would have like y1 prime, and then you would have y1 double prime, and then et cetera, et cetera. Right? You would just do the same thing with more derivatives and more equations. And the reason you do that is because it has to be a square matrix, right? So if you add a column, well, then you need to take more derivatives to add a row. Any questions about Wronskians? Yeah, Jake.
For like the y2 there, does that still work? You plug it back in as y.
Yeah, it would. If you plugged in y2 into this equation, like if you plug that in for y, it will work.
What if you plugged in c3x squared e to the negative of x? Would that work?
No, because you're second order diffq, so you'll never be able to kill the squared term. But here's you can kill the x term because you're first order. Even though you have the, we'll get to an example later on. I think you'll see it there. But essentially, yeah, you can kill terms with the x.
But it's just not arbitrary that we just throw it in.
Yeah, it's not arbitrary. Right. And then Kento asked about, okay, what if we had more multiplicity and repeated roots? So in general, if root r has multiplicity k, the solution associated with R is the following. You'll get C1 e to the Rx plus C2 e to the C2x e to the Rx plus C3x squared e to the Rx plus dot 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 all the way up to CK, right? Because your multiplicity is K, so you need to have K linearly independent solutions, okay? And then this will be x to the K minus 1, right? Notice that these powers are always one less than whatever solution you're on. E to the Rx. Yeah.
For the Wronskian, you said if you can find a particular x and make it 0.
It doesn't matter. It doesn't matter. The whole thing has to be 0. I'm pretty sure that's the case. I'm like 95% sure that's the case. I'll probably make a post on Piazza about that if I'm wrong, but I'm like pretty sure that's the case. The entire thing has to be 0. Because if you think of it, if we plugged in like e to the negative 5x and e to the negative 5x without the x, if you take that determinant, it's 0, right? So,
Is this sort of just like if we think about what we learned before, like that's why it works, plugging in why like taking multiple derivatives, like why exactly does it work?
why does it work? It's the whole like this, like if you have multiple equations, like so the function values, obviously if you add two functions you'll get like a third function, but if you add the derivatives of the functions at that point, you'll also get the derivative of this added function at the point up here. And the same thing applies for the other derivatives. So if they're all equal, then they'll be linearly dependent. Okay, so that was number 3. Number 4. Any more questions on this repeated root stuff?
So
Yeah.
if you have like one root with multiplicity 2 and one with like just multiplicity 1,
Yeah.
then like
This is for the associated R.
so just for the one with multiplicity 2 you did in this
Exactly,
one, and you
exactly.
tack on the
And you tack on the other one.
Okay.
Yeah. Okay. 4. Y double prime plus 6y prime plus 25y is equal to 0. All right. D squared plus 6d plus 25 apply to y is 0. So we can't really factor. Can't really factor this polynomial in D, so we got to do the good old -6 plus or minus the square root of b squared, which is 36, minus 100, that's 4ac, divided by 2. Okay, that's -6 plus or minus 8i over 2, which is -3 plus or minus 4i. So you want to think of this as a plus or minus bi, where a and b are like your constants. Okay, here's a wrong solution. C1 e to the -3 plus 4i t plus C2 e to the -3 minus 4it. It's really tempting to do this, and like it's like technically correct when like you're taking the roots and you're just putting them in, right? The reason it's wrong is because it can be simplified. All right, and so how do we simplify it? Here's the correct solution. So the correct solution for an a plus bi root is y of t is equal to C1 e to the AT cosine BT plus C2 e to the AT sine BT. So what is that in our case? In our case, that's C1 e to the negative 3x, or 3t, cosine 4t, plus C2 e to the negative 3t sine 4t. Yeah.
What if there are more than two roots?
So for complex roots, right, they always come in conjugate pairs.
Oh, okay.
So you always have this. Okay, so we can go through why this is the case if you want to, or we can just hand wave it and we can say this is it. I did it for the other classes, but it's kind of involved. But essentially, okay, we'll do a really quick why. Okay, this will be really quick. So let's say you have e to the, so we're not even dealing with the constants, but let's say you had e to the a plus bit. Okay, by the property of like exponential, like multiplication, this is e to the at times e to the bit. Right, because when you multiply exponents, you multiply exponential functions, you add the exponents. All right, but if we look closely at what e to the bit is, e to the bit is equal to, it's equal to cosine bt plus I sine bt, and that's like Euler's formula, right? It's I don't know if they introduced this in like 104 or something like that, but certainly not 114. But that's what e to the bit is. And so what you get then is you get like e to the at, right, times cosine bt plus I sine bt, right? And this is e to the a plus bit. And then e to the a minus bit, you'll get the same thing, except this is a minus I sine bt. All right, you can work that out at home. But essentially, you need to use the fact cosine of negative x is equal to cosine of x, and sine of negative x is equal to negative sine of x. So that's how you show this one. And then notice, right, up here we were taking linear combinations of these guys. So there's going to be like a C1 and a C2 times these. I can choose constants that will either kill the cosine term or I can kill the sine term. Right? So if C1 and C2 were both 1 and I added the solutions together, what happens to the sine terms? They go away, right? Because they're opposite sign, right? Likewise, if I chose C2 equals -1 and C1 is equal to 1, right, then the cosine terms go away. Okay? So the point is, like, I can choose constants that kill the imaginary part or that kill the real part, and therefore, when I look at my solution, I only need to take then the sine and the cosine term. And then the I gets eaten up by the constant. You can think of it that way. Okay, are we good here? Or is that satisfactory enough? Okay, so yeah, that's the important thing for complex roots to remember. Okay, so let's jump to then another problem. This is initial value problem. So here's the following. You're given y double prime plus xy prime plus 16y is equal to 0. But you're also given that y of 0 is equal to 2 and y prime at 0 is equal to 7. So these are initial value conditions. Okay, so those are initial value conditions, and they help you recover C1 and C2. All right, so they help you find those unknown constants in your solution. So how do we do this? Well, step one is always just to find the general solution with the constants. So, right, this is d squared plus 8 minus 8. Oh, let's make this a minus sign. All right, so minus 8d instead of plus, and we change it up there as well. Apply y is equal to 0. So that's d minus 4 squared is equal to 0. And so y of x, right, we have this repeated root thing again. It's c1 e to the 4x plus c2 x e to the 4x. Right, and that's because d is equal to 4 with multiplicity 2. Okay, so now what? Now, after we have the general solution, right, we can use the initial value conditions to solve for our constants. So for example, y of 0, right, that's equal to c1 e to the 0 plus c2. Right, now x is just 0, right? So c2 times 0 e to the 0. Okay, what is e to the 0? It's 1, okay? Don't say it's 0, that's a really tempting thing to do. So e to the 0 is 1. So this is c1, and the second term just gets killed by the 0, right? So now we have y of 0 is equal to c1, which is equal to what? 2, by the initial value condition given above. Okay, so now we see that c1 is equal to 2. Now we need to take derivatives. So now I need to take y prime of x. All right, so we got to go from there. Got to take the derivative. All right, so y prime of x, that's 4c1 e to the 4x plus, and now we got this product rule garbage going on, c2 e to the 4x plus 4c2x e to the 4x. All right, I'm just going to say this is my product rule. Okay? And so now we need to evaluate y prime at 0. Okay, so this is 4. So again, let's make the 0 some random color. So now this is 4c1 e to the 0 plus c2 e to the 0. And then what happens to this last term? It's 0, right? It gets killed by the x. So this is 0. Okay. So now this is equal to 4c1 plus c2. But what is c1? 2, right? We solved it above. So this is 4 times 2 plus c2. And what is y prime at 0? 7, right? It's in the problem. So this is all equal to 7. And so now we see that C2 is equal to negative 1. And so our final solution then is y of x is equal to 2e to the 4x minus x e to the 4x. Is the solution to the initial value problem. Okay, any questions?
Does that homework include any non?
I don't think so, unless the 2 problems he added yesterday. So I know in class he's been doing like dy dx plus y is equal to some f of x, right? And then, but notice that this is just a first order differential equation, right? It's not a second order, and everything we did today was second order diff EQs. So the reason why he's going through first order diff EQs is because you can solve these by integrating, right? Which is why he talked about the whole integration factor and all that stuff. So it'll come up in a particular application later on, but he's just introducing it now, I think. And then all your homework is essentially second order diff EQs that are homogeneous. So that's what you guys are doing in class. It has applications later on, but this is what your homework is. So, all right, I have exams, and I think homework's due on Tuesday. Office hours today. My class at noon got canceled, so I'll be in my office pretty much all day. So email me if you need to stop by. I'll more than likely be there. So, all right.
Why does the book use R instead of D?
Oh yeah, I said that earlier, but I think it was before you got here. But I was just like, they just make the substitution that just like they just call it different.
Just because it says not like the derivative
So
operator?
yeah, exactly. So it's
Okay.
not like the root of the operator is
Yeah.
something that doesn't really make sense,
Okay,
but
okay.
like doesn't
It
really matter.
Okay, thank you.
Also, I think I never took the midterm.
One. Okay, I have it.
Oh, really?
Yeah, it's in my office downstairs.
Oh, wait. Can you
Do you have
next
class?
recitation?
Yeah, I can try to remember.
Okay,
Maybe if
if
you
you
send me an
don't-
email,
Okay.
I'll remember.
Is it?
Left. Yeah. There's Pablo. Steve. Right.
Thanks.
David, your picture's up, right? Okay. Yep.